All right. Well, we're very happy to have Austin Batz from University of Oregon by way of Berkeley is going to tell us about dark mesons stopped in their tracks.
Yeah, thanks for the introduction. And yes, so I am in my last year of PhD at University of Oregon, and I'm spending that on a DOE fellowship at LBNL. I'm going to tell you about some work that I put out recently with Puya Asadi, Elias Bernwitt, Marco Costa, Sam Hummler, and Graham Gribbs. I don't know how I accumulated so many collaborators, but here we are. Yeah, so I'm going to tell you about dark mesons. And first I'm going to say some very general words about confining dark sectors. And so the idea is very simple. You just add some non-abelian gauge group that confines at low energies. You have some dark quarks and dark gluons, and you have some number of colors, some number of flavors, not necessarily 3. And in the IR, you get a rich spectrum of dark hadrons, mesons, baryons, etc., with many different possible portal interactions with the standard model. And people have used these kinds of dark sectors in order to solve problems like dark matter, the hierarchy problem. It is a very general setup, so you can do with it what you want. But I mention this because, as we enter an era where the simplest answers to the questions we don't know yet are sort of strongly constrained or ruled out, it becomes interesting to think about non-minimal solutions that have some natural mechanism to stay hidden, which confining dark sectors often have. So now, what is our theory specifically? I mean, it's just about the simplest dark sector you could ask for. You have some dark gluons, you have some dark quarks. And for us, our dark quarks will be vector-like, and they will transform in some representation of standard model SU2 left. And what we're calling the number of flavors is the dimension of that representation. So NF is our number of flavors. And lots of people have studied this kind of dark sector, often in the context of dark matter. There's a conserved baryon number in the dark sector, and so it's kind of natural to think about a dark baryon being a dark matter candidate. For us, it will be important that nothing in the dark sector has hypercharge, and it will be very useful to think about SU2 left as a gauge subgroup of an SUNF flavor symmetry. And now to bring this into some more recent context, this particular model has been the subject of other recent work where some very key observations were made about the dark baryons that arise at low energies. And in particular, you might think, well, if the dark baryon is dark matter, then it is some composite made of charged constituents, and so obviously it will have some electromagnetic moments that will very strongly constrain it. But in this particular case, that ends up just not being true. And you can see that because there's this natural Z2 called H parity, which I will talk about more later, that forbids those electromagnetic moments. And you can read more about that in this paper. And so the leading direct detection signals, if this is really the dark matter candidate, end up being these electroweak loops, which themselves are fairly suppressed. Then there was an additional observation made in this paper that very often, and by very often I mean for a lot of combinations of number of colors and number of flavors, the lightest dark baryon in the spectrum is a total standard model singlet. And when that is the case, you don't even have these diagrams. And so your potential direct detection signals are even more suppressed. And this is the situation we call noble dark matter, in analogy with noble gases, because you have some composite with charged constituents that just so happens to really not like to interact with other stuff. Yes?
So can I just at some order, these objects, if they have charged constituents, they would have some moments, some electromagnetic moments, right?
Absolutely.
And the claim is that those are really small. So even though those are like one photon exchange, so they're long range, or not actually, I guess they won't be long range, but anyway, they're one photon exchange, and those are suppressed in direct detection?
Yeah, one photon exchange is absolutely suppressed. So the next unsuppressed thing would come from higher dimension operators like polarizability,
Right.
which is 2 photons.
There wouldn't be anything if one photon is somehow, is it a sort of an effective charge conjugation? Does the H parity act like charge conjugation on the photon?
Basically,
I see. So that sort of forbids any one photon exchange
That's
thing.
right.
And then you have 2 photon exchanges.
That's
It's just not clear to me why this electroweak diagram would be the one that dominates, right?
Over polarizability?
Yeah, over,
Well, polarizability, particularly in the non-relativistic limit, is super suppressed.
so it's more powers of velocity versus
Yeah.
here it's like powers of energy over MW.
Yeah.
And the claim is that these things still win.
Yeah.
Okay.
Yep. Other questions? Okay. Great. Yeah, so I'm going to talk about the dark meson spectrum much more than the dark baryon spectrum in this talk, because that's the focus. And I'm going to spend a lot of time talking about what are the mesons in the theory, how do they interact with the standard model, how do they decay, how can we probe them. I'm going to talk about a chiral anomaly that only pops up for very specific species of the mesons in the theory. I'll discuss collider signals and the constraints we can draw using those before concluding. Okay, so what dark mesons show up? Well, we are going to work in the limit where the dark quarks are significantly lighter than the confinement scale in the dark sector. And the confinement scale, let's say, is order at least TeV-ish. And so what that allows us to do is work in the effective field theory of mesons, and we can trade microscopic parameters like the quark mass and confinement scale, etc., for parameters in the low energy effective field theory, like the dark pion mass or Linus dark pion mass, and the dark pion decay constant, f pi, and then 4 pi f pi sets the scale, the characteristic scale of the EFT. And then we have chiral symmetry breaking in the standard way, where you have some UNF cross UNF that gets spontaneously broken to a vector SUNF with a U1 of baryon number. And that results in like-ish pseudo-goldstones, like-ish because there's plenty of explosive flavor breaking. And then each meson, because it has constituents that are charged, each meson will transform in some representation of standard model SU2 left. And figuring out what those representations are is a fairly trivial group theory calculation, because we know what the representation of the quarks are. And so we can see that the pseudo-goldstone representations will be a 3, a 5, etc., and the number of them that you have depends on the number of flavors. So if your number of flavors is 2, you only have a 3. If it's 3, you have a 3 and a 5, and so on. And then the 1, we can identify with the dark beta prime, which is the would-be goldstone of the anomalous axial U1. So it's the not goldstone of the not symmetry. Okay. And as I alluded to before, there are these important Z2s. We have a whole zoo of them that act on various states in the theory. And those are H parity, charge conjugation, and G parity. So H parity is what I was referring to before. It is a global SU2 left rotation. So JY is the second generator of SU2 left. And it acts on the quark fields in this way. And what it does is it maps particles to other particles in the same electroweak multiplet in the dark sector. And H parity is the thing that forbids the neutral baryon electromagnetic moments. But in the context of mesons, what ends up being much more important is G parity, which is something you might have heard of. Yes.
So J refers to the SU2 left generator.
Yeah.
Right.
Yep.
Okay.
Right. So,
So this just flips the multiplet.
yeah, it does. It does. Right. So then G parity is simply the composition of charge conjugation and H parity. And this has an analog in the standard model where in this rotation, instead of an SU2 left generator, you have an isospin generator. And that leads to certain selection rules for the mesons in the standard model. So the pions are G odd and the etas are G even, etc. But for us, G parity will be the dark G parity. Will be even stronger than the G parity in the standard model because in the standard model, G parity is broken at tree level by electromagnetism. Good. So, how do our different meson states transform under these different Z2s? Well, as John pointed out, here I'm labeling a meson state by J, so that determines the representation under SU2 left, so it's in the 2J plus 1 dimensional representation of SU2 left, and the electric charge. And so what H does is it takes a particle to another particle in the same electroweak multiplet with opposite charge up to a sign, which you can show that sign is given right here. And then charge conjugation does a very similar thing. It'll take a particle to its antiparticle, but for the meson species, the particles and antiparticles are found within the same electroweak multiplet.
Sorry, just a little confused. The setup, is the setup here that you're assuming that so in a vector-like representation, is it just a bunch of doublets or you're being more general? I'm confused if you're being more general, I'm confused about why you don't have a more complicated decomposition.
No, there's one sort of generation. So there's one SU2 left multiplet of dark quarks. Does that answer your question?
There's just one.
There's one.
And then there's just the dark color and that's it.
That's it.
So once I confine, so there's two, so that means that from the point of view of the strong extra sector, there are two flavors.
There's a bunch of singlets.
There's a bunch of singlets. So there's one doublet, there's one electroweak doublet and a bunch of electroweak singlets. I'm just trying to understand
no.
what the model is. I'm sorry, I'm still confused about what the model is.
No, that's great. Yeah. So
I had the impression you were talking about something much more general than, anyway, what is the model?
yeah, so this here is in just some representation of SU2 left, right? So it's not necessarily just a doublet in a bunch of singlets.
Could be reducible, could be irreducible, could be anything.
Here it's an irreducible route.
Irreducible.
It's an irreducible.
Okay, so in an irreducible, and there's no singlets?
No.
Okay,
No
it's one
singlets.
irreducible SU2 multiplet.
Yep.
So it can be like a symmetric tensor, right?
If you like.
Yeah, okay,
Yeah.
I got it. All right.
Yep.
All right,
And,
thanks.
and NF is the dimension of that representation.
Perfect,
Yeah.
got it.
Okay, great. Great. So yeah, so charge conjugation here does something similar to the H parity transformation for mesons in that it takes a meson in some electroweak multiplet and maps it to another meson in the same electroweak multiplet with opposite charge. And so when I compose these two to get the G parity transformation, I go from a meson state to the same meson state with a sign that depends on, well, S and L are the spin and orbital angular momentum of the mesons, which we're not going to care about right now, so you can think of them as 0. So otherwise, it depends only on the representation of the meson. And what that tells us is that not only is each meson species an eigenstate of G parity, each electroweak multiplet of mesons is an eigenstate of G parity. Okay.
Sorry, is the charge here the eigenvalue of the third generator of SU2L?
Yeah.
Okay.
Yep. Electric charge. Yep. And there's no hypercharge, so yeah. Okay. So now I'm going to write it out somewhat more explicitly. So again, we have a triplet a 5-plet, a 7-plet, etc., depending on how many flavors you have. And the G parity of each of them alternates, odd, even, etc. And as you go up, of course, you get more and more charged mesons in each multiplet.
The G parity, is it sort of flipping the multiplets then? What does it do to the members of the multiplets?
G parity does not. G parity
G parity
leaves it
doesn't.
alone except for a sign.
Okay,
Yeah.
all right.
H parity will flip it around.
It's just a Z, just an overall Z2 sign,
Yep.
that's it, okay.
Yeah, for the mesons, yes.
All right,
Okay. Whereas for like a baryon state, G parity would map it to an antibaryon.
okay.
Yeah. Great. And then each of these multiplets gets corrections to its mass from electroweak loops, and the size of that correction depends on the size of the representation. And so as you go to higher representations, you get stronger mass enhancement. And likewise, due to electroweak symmetry breaking, as you go higher in charge, you also get separations in mass. So this pi30 will be the lightest one, followed by the charged ones, and so on. So now let's talk about decays. Since we have this G parity, that will severely limit what kinds of decays you can possibly have. So in particular, the charged 3-plet can only decay to something else with odd G parity that is lighter than it, and there's only one option, and that is the pi30. And it will do this by emitting an off-shell W that effectively mixes with the standard model pion. And there's a very small phase space for this to happen, because the mass splitting between these is only due to a loop with a photon. And so there's like a roughly 170 MeV mass splitting between them.
Sorry, I'm just confused again, I'm just being slow.
Yeah.
So if you, can you just go back again, I'm sorry. So just to the thing where you have with the G parity action on the, one more, yeah, there. So these J's are the J's that when you do the decomposition, there are multiple J's, right? In the J's are labeling the meson irreps of
Yep.
SU2,
Yep.
and so there's a whole list of those things.
Yep.
And so when you're talking about the neutral guy, there's actually a neutral guy in every multiplet. Every
Yep.
one of those, yeah, okay.
Yep.
So those are all there at the same time.
Yep.
Got it, up to some maximum.
Yep.
Okay, thanks, sorry.
Other questions? Yeah, our referee said we had too many small details, so.
No, it's, I'm actually, because I'm actually able to follow it, so I'm actually going to try to follow it, so I'll ask these picky questions.
Yeah, that's great.
Thanks.
Okay. Great. So for the charged 3-plet, this kind of decay process is the only thing that it can do. And because it has a small phase space, it will have some macroscopic lifetime.
So again, sorry,
Yeah.
picky question. So some of these J's are even, some of them are odd. So some of these multiplets are G parity even and some that are odd. But when you're saying it can't decay any other way, is that true even for what about the G even multiplets? They can decay easier?
We'll get there.
Okay, we'll get there. Good.
But short answer, yes.
Okay. Yeah, the G odd ones.
Yeah, the G odd ones are, yeah. Okay. And as you say, since this pi30 is the lightest G odd one, any decay of that one will violate G, which, given the model I've handed to you, can't happen at dimension 4. But if I have some UV completion, then I can write down some dimension 5 operators that do violate G. And so if I have that, then generically the pi30 decays will be allowed, but potentially very strongly suppressed. Okay. So now to those higher representations, the 7, the 9, etc. Well, if you just expand out the chiral Lagrangian, including all the electroweak bosons, then you'll see these 6-point vertices in here. And because I can close the loop, I can have these sort of effective 4-point vertices between the different mesons, plus a pair of electroweak bosons. So here we have, some meson, some other meson that is of the same G parity, and 2 electroweak bosons.
So, just again, so that means you're writing this loop diagram because the tree level diagram without the loop doesn't exist.
Mhm.
That's a 2 derivative order. So this loop is presumably equivalent to some 4 derivative operator that you could have written that you could have written in the chiral Lagrangian. Is that right? So there are 4 derivative operators that also induce this mixing at the same level. Generally, I would expect, the reason I'm saying that is generally I would expect one loop pion things would renormalize, logarithmically generally renormalize 4 derivative things. That's the generic sort of structure. So I would expect there would be 4 derivative terms in the chiral Lagrangian that would do the same thing.
4 derivative terms?
Yeah.
Well, those will also be non-normalizable.
Yeah,
I'm not
they're-
sure I understand the...
It's okay. It's a
Okay.
detail. Let's not get hung up on it.
Okay. Anyway, what these do is they allow states in the higher representations to decay to a state in the lower representation by emitting 2 electroweak bosons. Okay, so now the 5. The 5 is very special. And we can see why it's special by writing down the chiral anomaly operator that appears in the chiral Lagrangian. And we have the sort of standard form here, where we have the non-abelian field strengths of the SU2 left bosons, and we have this trace over 3 generators. And the 3 generators in here, one of them indexes, which meson am I talking about? And the other 2 are SU2 left generators. And since we can think about SU2 left as a gauge subgroup of the flavor symmetry, we can think of all of these generators as they have the same indices, and so this trace does not factorize, and in general it doesn't vanish. But I claim that the 5-plet is the only pseudo-Goldstone for which this does not vanish. And you can see this because if this guy were in some higher representation, like a 7, a 9, or whatever, then I can't make this operator gauge invariant. It just doesn't work. You can't make a singlet out of those. And if this is the 3, then just by the symmetry structure of this trace, that also vanishes. So there's only one option. It has to be the 5. And for the 5, it is not 0. And we can just write it out very explicitly. I've only written it out to show you that you can. Right? And so we have each component of the 5-plet interacting with pairs of electroweak bosons, and so on. And you can see here there is explicit dependence on the number of colors, and there is explicit dependence on the number of flavors that comes out of this trace. You can evaluate this trace for the 5-plet in complete generality for whatever number of flavors you want, and it's a cute calculation to actually derive this. We have it in an appendix. But conceptually, you can see that it scales like NF to the 5 halves. And so the strength of this anomaly interaction increases fairly quickly as you increase the number of flavors. But the interesting piece here is that processes in the low energy effective field theory give you insight into parameters of the UV EFT, NC, and NF. And this is kind of similar, well, it's extremely similar, to measuring the standard model pion decay rate to photons as an early way of seeing that there are indeed 3 colors in standard model QCD.
Sorry, so this 5-plet is G parity odd?
Even.
Even.
Yeah. Oh, I should have said.
Sorry, okay, that makes sense.
I should have said explicitly the...
Yeah, you did say it, it's just, yeah.
Yeah, everything with a pi is G odd, everything with an eta is G even.
Oh.
As a sort of loose analogy to the standard model. Yeah.
So my math is bad. The reason you have 5 that only works is because as you do have only 3 generators and somehow you have 2 generators here, and how do you get 5 from 3? Or is that not the reason? So why does that term only work for a 5-plet?
Yeah, so maybe I should write it down.
I mean, it won't work for super high representations at some point because it has to be found, the W's are in fundamentals of SU2. So it has to be in the decomposition of SU2 cross
Yeah.
SU, right? Two triplets, they're
Yeah.
triplets,
Yeah, so
right? So it can't be an arbitrarily high representation.
Well,
Yeah.
W's contract with J.
Yeah,
Here, so
Yeah.
I'll show you.
yeah.
So I have a meson in some D,
Yeah.
and I have 2 3s.
Because now you have the
Because I
W's.
have 2
Yeah.
W's.
Yeah.
3 times 3 is 1 plus 3 plus 5.
Okay. Yeah.
When I multiply in this D, I can only get a singlet if D is a 1, a 3, or a 5.
That is true. Yeah. I see.
If D is 1, that's the eta prime. That's not a PMGB. If D
Yeah.
is 3, the index structure works out so that there's enough anti-symmetry that this cancels.
Okay.
The only thing left is a 5.
I see.
So that's the only option.
Yeah.
That's okay.
We're very annoying, so.
No. I want you to ask a lot of questions. Are there any other questions up to here? Okay. So, what does this allow you to do? Well, I'm able to couple a new scalar to pairs of electroweak bosons. So this has obvious pheno implications of the LHC. And in particular, not only is the 5-plet allowed to decay to pairs of electroweak bosons, it can also be resonantly produced by pairs of electroweak bosons in a vector boson fusion process. And so you can just look for that. Okay, so we've reviewed a couple of times, but just to make sure we're all on the same page, we have several species of pseudo-goldstones. We have each odd representation up to however many flavors you have. So for all numbers of flavors, you always have a 3. For at least 3 flavors, you also have a 5, and so on. They alternate G parity, so pi's are odd, etas are even. The charged pi's cascade decay, and so they emit a standard model pion and go down to the pi 0. And any decays of the pi 0 would violate G, which I haven't given you a theory that does that. The 5 decays by anomaly, and the higher representations decay by hopping down to a lower representation.
So if I tried to make a kind of slightly perverted spectrum where the eta 5 was heavier than, say, the eta 9, and probably that's not impossible. But then there's a little bit of a mystery because how does eta? I guess you're thinking eta 9 would just decay by mixing through the eta 5, right? It would still decay then just by virtual mixing.
Yeah, you could do
So there
that.
would be no okay.
Yeah, you would have to kind of carefully engineer the situation though, because the,
Yeah. No, it's just okay.
yeah.
Mm-hmm. Okay, thanks.
And you might accidentally break G parity in the process, but anyway, sure.
Mm-hmm.
Okay. So now that we know what the theory is, we can finally start talking about phenomenology. So at the LHC, we can particularly focus on the 3 and the 5. Each of them has very striking signatures. In particular, because the charged 3 is a long-lived particle, and the 5 is a scalar that you can resonantly produce. And so there are existing searches that place very strong bounds on this theory. So we can produce the 3 by a combination of Drell-Yan and vector boson fusion, and the charged one is long-lived. The neutral one, at least in this talk, is collider stable. And the signal is disappearing tracks, which I'll talk more about in a second. And of course, the 5 is all through the anomaly. So, that 3. Again, I can produce it through either VBF or Drell-Yan, and it will decay after some displacement. And this is analogous to the classic signal of chargitos that appears in some manifestations of the MSSM, where you have basically the same scenario. You have some charged triplet that has some small mass splitting with a neutral component. It decays by emitting some soft pion after some displacement. And so what you have, and the soft pion is not reconstructed. So what you have is a track that appears to just stop inside of the tracker. You might even say it stopped in its tracks. So this is something you can get out of supersymmetry, and so there are existing searches for it. Very, very powerful searches. Good. And just as a side note, there's a reason why I keep stressing that this can be produced by both vector boson fusion and Drell-Yan, and it's because the Drell-Yan cross-section plummets very quickly as a function of the mass, which is in part due to this S-channel propagator. So you might have thought, oh, VBF in its higher-order perturbation theory is going to be more suppressed, but no. It is strongly dominant. Which would have been easy to forget. Okay, so we apply these bounds. And what we did was we basically just reused a reinterpretation software package that somebody had already come up with for these disappearing track searches. And that software package was originally designed for an earlier search, an earlier Atlas search, which we basically just did a luminosity rescaling to recast for a more recent search. But the point is, these searches are so good that you can put a bound on the triplet pion mass of about 1.2 TeV, independent of other model parameters.
So I guess I'm just thinking through this thing, the comparison with Drell-Yan and VBF. I mean, for quote unquote normal signals, Drell-Yan usually often, I mean, some of the highest reach searches are of course like Drell-Yan production, like Z primes and things like that. And that's because of the signal versus background, right? But here the point is these signals are sufficiently exotic, right? You don't have huge backgrounds, and so you really are taking advantage of the higher rate.
Yep.
Right. Okay.
We started part at the 200 GeV, change the lighter and 200.
Well, not according to this spec, right? I don't know if that answers your question, but
So you cannot, you just say.
right. So I mean, the lower bound on the mass from here is like 1.2 TeV. So we
This
don't.
is the 7th search I just didn't add it to lower mass. Or
Down to 200 GeV.
Huh?
Yeah, down to 200 GeV. I don't know. Does that answer your question?
No, I say, can they be 150?
Oh, can they be 150? No. Yeah. This applies to lower masses as well.
Okay, you just didn't
That's
add
right.
it to
That's
the lower mass.
That's right. Yeah. It's an
Your
arbitrary
file
cutoff.
is-
Yeah. Okay.
So for your pi 3, the cross-section is fully determined by the standard model couplings.
Yeah.
With the only... So what's the interaction rate Lagrangian for this one?
Sorry.
Just electroweak.
The electroweak
It's
one.
it's entirely electroweak. The only portal we have is electroweak here.
So you just couple to the same electroweak G prime or G1 or G2 or one of the G's. Okay.
G2. Yeah. Okay. So that's basically the story for the triplet. For the fiveplet, things are quite different. We can produce them as a resonance, also by vector boson fusion. And depending on which component of the fiveplet you produce, you can get several different possible final states. So the doubly charged one will go to same sign W's. The singly charged one will go to a W plus either a photon or a Z. And the neutral one has more options. And it turns out that the best constraints will come from the same sign W's, opposite sign W's, and either diphoton or diz. And a scalar that is produced by VBF that decays to 2 electroweak bosons is an obvious thing to search for, and so there are lots of searches that already exist for these. And several of these have very clean signals, particularly diphoton, and so they can probe down to quite low cross sections. And here's the result. So here what I have is a constraint in terms of the mass of the fiveplet, and on the vertical axis I have 4 pi f pi as the characteristic EFT scale over NC, and this is the combination that appears in the anomaly operator. So this sets the strength of the anomaly. I've picked NF equals to 4 just to pick something.
Is it really f pi over NC and not f pi over root NC?
It's F pi over NC.
Because I thought in large NC limit f pi is, oh no.
F pi goes like root
F
F.
pi goes like root NC.
Yep.
Okay.
Yep. Yeah. This
Yeah,
just
okay.
comes from reading off. Reading off
I
here.
believe you. I'm just
Yeah.
testing my own knowledge.
Yeah.
Okay.
Okay.
Yeah.
So, right. Yeah, I picked NF equals to 4 here, but you can rescale by I for other values of NF. Again, the fiveplet is only in the spectrum if NF is at least 3. So here, you might see, well, these bounds all seem pretty close to each other from the different final states, diphoton, diz, and all of the others, but here it looks like diphoton should be the best, right? But that is because the photon is mostly the beam, and so you get suppression from the sign of the Weinberg angle. And so all of these kind of scrunch down to similarly good bounds for the different possible final states. And I should have said, because the labeling is somewhat confusing for here, this black ZZ contour is for the ZZ final state in the fully leptonic channel, and the W plus W minus slash ZZ is a combination of those in the semi-leptonic channel. And so, we also did a projection for the high luminosity LHC by just taking the best expected limit from each of these and rescaling it to 3 inverse attobarns. And you can see that there is potential for really significant improvement in probing this space, up to multi-TeV, 5-plit masses, and even more multi-TeV f-pi's. And, sorry, go ahead.
No. Well, I was just going to ask about the shaded region on the left. Maybe
Yeah, that's exactly what I was going to say.
Okay.
So we know that the 5-plit is heavier than the triplet. We don't quite know how much heavier, but we know it's heavier. And the triplet has this already existing bound that we discussed before. And so however much heavier the 5-plit is, it's definitely going to be heavier than this. And so that allows you to impose this vertical line. And again, I should have said, these EFT breakdown contours for different values of NC are where the eta mass becomes equal to 4 pi f pi and you're working along EFT.
So you're assuming that the mass splittings are coming entirely from electroweak loops?
Yep.
So doesn't that mean that in principle you know exactly what they are?
Well, not exactly, because there's still some implicit dependence on f pi, right? The loops in question are quadratically divergent.
Okay, yeah, in
Yeah.
terms of f pi.
Yeah, in terms of f pi, you can do it.
So you actually
up to EFT scale.
well, if NC was 3, for example, right?
Yeah.
There's the operator that gives the electromagnetic contribution to the mass is measured, right, by the real world. So you could rescale it to this case, right? So there's an operator in the QCD effective chiral Lagrangian, right, that gives you the electromagnetic splitting of the pion mass. And then, well, I guess it depends on NF. I mean, anyway, I would say that you pretty much know the not just qualitatively, but quantitatively, you know the spectrum up to I guess f pi.
Yeah, I mean I would say we know it with sort of within an order 1 factor.
Yeah.
involving f
Yeah.
pi. Yeah. And order 1 factors are important here, right?
Right.
Yeah.
I usually when we think the same sign will be easier to search for.
Yeah, I don't have an explanation for why the same sign W's are so much worse. Maybe they just put fewer resources into it, but yeah. I don't have an explanation for that, but that's what they quote. Yeah. Okay. Any other questions before I move on?
So I might miss it. What is the 3 angle bar minus 1 projection?
Oh, so this just comes from a luminosity rescaling of these other bounds.
Yeah.
Right.
I don't know.
Yeah.
And I thought if you go higher, it's less sensitive because the coupling is bigger. Or
It's just luminosity. If you're just running longer,
Yeah.
it's getting more data.
You are ruling out the region below, right?
Yeah, ruling out the region below. Yeah, so this was potentially confusing because here, these are upper limits in here. Right.
so F is in the denominator in your coupling, so that's why.
Yeah.
Okay, I see.
Yeah. Okay. Good. Okay, so there's more that can be done in this area. In particular, one is looking more closely at these potential G-parity violating decays. Because again, you can deal with dimension 5 operators, and so you have a lot of options as to how long that lifetime could be. And in particular, if it is detector scale, then you could get a similarly exotic signature where you have a disappearing track that itself points to a displaced energy deposit somewhere else in the detector. And that would be very interesting. And then if you could measure that, then you could probe the UV scale that suppresses those dimension 5 operators. And also here, so far, this whole talk, I've been implicitly assuming that your F pi is big enough that the only mesons we need to worry about are the lightest ones, the PNGBs. But if it were slightly different, if F pi is a little bit lower, then the higher meson resonances matter more and more. In particular, the spin 1 dark mesons. And those can mix with electroweak bosons and lead to all kinds of interesting signatures as well.
And just ask, I mean, qualitatively, right, these mesons are all pretty closely spaced, right? I mean, they're getting their splittings entirely from electroweak loops, right? So there's kind of a, to first order, 0th order, whatever, they're all degenerate or they're all massless, and then I guess that's the thing, yeah, they're all massless. So they're getting their mass from, So they're not actually closely spaced. Sorry, they're not, right? They're actually sort of, because they're getting all of their mass from this, right?
Yeah.
But actually your very first slide, you had a common mass for all of them?
For the quarks.
For the quarks, I know, but that would also give the mesons a mass, right? Just like in the
It does
QCD
contribute to
Lagrange.
the mass, yeah.
So actually, there's a regime where it depends on which one dominates. Like, right, in QCD, they're somewhat comparable, but roughly the quark masses, even for the pions, kind of, right, dominate. And so that's why they really, the pi 0 and the pi plus minus are, you know.
Yeah.
So you could be in that regime, or you could be in a regime where electromagnetic mass is everything. What I'm wondering is if you have the case where it's more compressed, a more compressed spectrum, is it possible that there might be some absolutely stable other things? I mean, you know, like I know that, for example, in the gluon spectrum, right, for just SUN, Yang-Mills theory.
The glue ball spectrum?
Glue ball spectrum, yeah. There's like 4 stable states. There's just some accidents, right? Because there are other quantum numbers.
Right.
You've identified G parity. I'm just wondering, are you sure that, are there any, do you know for sure whether any of the other ones might be stable as well? Strong, stable, you know what I mean? How confident are you on a scale of 1 to 10?
It's an interesting way to phrase the question. Yeah, I don't think there are other absolutely stable ones, but yeah.
You're being recorded, so you don't need to give a number. I'm just trying to get a sense, you know.
Yeah, no, I see your point. I see your point. I would have to think about it more carefully, but I think we're okay.
Okay.
Yeah. Okay.
Pi 0 can be stable, right, if you don't have any G-violation. Okay. Do you have to have G-violation?
Excellent question. So, one thing that absolutely could violate G is gravity. And if these dimension 5 operators I showed earlier are suppressed by the Planck scale, then that is very dangerous because the pi's are long-lived enough to survive BBN, but too short-lived to be safe.
The argument is just there's no global symmetry, right?
Yeah.
You know, there's no other.
Sorry.
Just by that, John never believed that. So if
Well, I mean, if you don't buy that, then like, sure, you don't need to introduce other operators, right? And then the pi tree then this one would be absolutely stable. But you know, if there are Planck suppressed operators,
but can you gauge it or not?
Can you gauge the dark G parity?
Yeah.
Maybe. You might have to gauge charge. Anyway. Maybe that's for offline, but anyway. Point is, if these dimension 5 operators do appear and are Planck suppressed, then you definitely need some other less suppressed dimension 5 operator in order to facilitate the decay before BBM. Yeah. Does that answer the question? Yeah. Okay, so then wrapping up, just to remind you, we have some confining dark sector. The constituents of that sector have some electroweak charge. They come to SU2 left. You get a rich spectrum of dark mesons and other dark hadrons in the IR in various representations of electroweak. For the mesons, that calculation for what the representations were is quite trivial. For the baryons, it is more subtle, and for that you can read the other paper. But for the mesons, we have a long-lived charged triplet, at least quasi-stable neutral triplet. And the 5-plet has a very special anomaly that is unique to the 5-plet among the pseudo Goldstones. And there are long-lived particle searches for disappearing tracks that impose a strong constraint on the 3-plet. And the 5-plet has some existing constraints, but at high Lumi they can probe a significantly larger region of that parameter space. And then there are some other opportunities for exotic collider signals using these mesons. And that's it. Thank you.
do you have some, like, pictures of, sorry, let me ask, let somebody else ask questions. I've asked a lot of questions, so anybody besides me have any questions?
So for them to be stable and live longer than the age of the universe, what's the constraint on this model? The mass shouldn't be too big than something?
For the neutral triplet,
Yeah, that would, if this is dark matter, that would be your dark matter, right?
well, the dark matter we would probably prefer it to be the dark baryon, but if that one is absolutely stable, in other words, if those dimension 5 operators aren't there, then it would contribute to the dark matter abundance. Other questions?
So I was just going to ask if do you have some, there's a lot of mesons here, right? So do you have some picture of the spectrum that would help me to, like this model, I could say it looks like supersymmetry. It's got a ton of new states. They can cascade into each other. I could imagine very, very complicated phenomenology. You're considering a case where, most of that stuff is just really heavy, or why, so these really are just the lightest states, and everything else is significantly heavier, and that's why you don't need to think about it.
Yep. Or at least heavier enough that maybe these signals are dominant.
I mean, you could, like I said, I think you could be in a compressed regime if you wanted to be.
A little bit more compressed, yeah.
And so then you could have even more complicated phenomenology if you
Sure,
wanted.
absolutely. Yeah. For example.
Yeah.
Yeah.
Okay.
Yep.
When you draw a track, is that up to scale? Do we expect the pion to decay with low enough energy so it curve with a small radius, or?
Yeah, this soft pion.
Yeah.
I believe that's right. I didn't make this diagram. This is not this diagram, but yeah, I think that's right. I mean, the point is it's very soft. Yeah.
I talked to an experimentalist who called diagrams like this Adobe Gen. They're generated by, Adobe by drawing, not actually generated events.
Right.
But that very dark matter, just you need a symmetry to get, to have the right relic density. I just think, I don't know if it's yours or some of the, they think about a symmetry.
Yeah, the relic density is something that definitely needs more attention. You could be in a regime where you have some asymmetric dark matter, and the symmetric component efficiently annihilates, and whatever is left is your asymmetric abundance. In other versions of this model, you could also have like a squeeze out process. I don't know if you have encountered that, where in the confining transition, a huge portion of the quarks and antiquarks annihilate each other. Anyway, long story, but the point is there are different possible mechanisms to set the dark matter abundance, and still needs to be worked on.
You're saying if you allow the asymmetry, there's an asymmetry, and that's a free parameter, then
Exactly.
you can get anything.
Yeah. Which I know is unsatisfying, but
If pi zero is stable, what do you expect to relic density? Do you expect too little or too much, or roughly right?
yeah, I don't know. Yeah, it's a good question. Did you have a question?
Yeah, so I heard before that there's other ways to get these displaced vertices through dark photons or similar things. Would there be any way to differentiate something like this from a different mechanism causing this displaced
Well, I mean, of course, displaced vertices in general can be caused by lots of things. Here, what's very interesting is that you not only have a disappearing track and a displaced vertex, you have a disappearing track that points to a displaced vertex, right? And that's a fairly exotic object. I mean, surely you can come up with other models that do this, but yeah.
Like split Susie or something.
Sure.
Because they also have, because it's coming from the fact that you're emitting this very light particle, right? This light pi. So
Yep.
split Susie would have that qualitatively at least.
Sure.
But I mean, just following up on Cincha's question, I mean, I would guess that, this pi zero, everything is sort of electroweak, right? It's a TeV, it's got, order one couplings and units of TeV, so the dark matter abundance is not going to be ridiculously off. It seems like it is worth calculating. Maybe,
Absolutely.
right? Because it could be, even if you don't know all the parameters, I mean, it seems like it's in the right ballpark, roughly.
Yeah, absolutely.
So maybe worth doing.
Absolutely.
All right. Let's. I suggest we thank the speaker and keep grilling him off camera. All right. Thank you very much.